to the Ocean Insights Seminar Series, which is organized by the Early Career Scientist Network of the Indian Ocean Expedition. Today we have a combined talk presenting an overview of marine heat waves in the Southwest Indian Ocean, presented by Dr. Daneeja Mawren and Clea Welch. So Daneeja is currently a postdoc at the University of Cape Town and the South African Environmental Observation Network. Daneeja completed both her master's and PhD studies at the University of Cape Town and has published a lot of literature on marine heat waves and extreme events in the Southwest Indian Ocean and the Mozambique Channel, looking at the impacts and drivers of these events. And Clea is currently a master's student at the University of Cape Town as well. And she's looking at the subsurface characteristics of marine heat waves in the Mozambique Channel, which is a continuation of her honors project, which she also completed last year at the University of Cape Town. And it's a really nice opportunity to combine these talks so that we have a full overview of marine heat waves, including the drivers and the impacts, as well as the subsurface. And so everyone knows that this talk is going to be recorded and going to be uploaded onto YouTube, as well as just ask if anyone has any questions, please feel free to put them in the chat. Daneeja is going to present first, and then Clea is going to follow. And I think we're going to take questions right at the end, just to not break the flow of talks. So if you have questions, please feel free to post them in the chat. So Daneeja, over to you.
Thank you, Matt, for the introduction. I hope you can see my screen. Is that fine?
Yeah, it's perfect.
Perfect. So hello, everyone. So for today's talk, I'll be giving you an overview of the work that I've been doing in the past few years as part of my postdoc, looking at the drivers of marine heat waves in the Southwest Indian Ocean, how they co-occur with tropical cyclones, and also the influence of large-scale climate modes on their evolution. So to start, we'll give you a little bit of background on marine heat waves. So based on the Hobday definition, these extreme temperature events occur when ocean temperatures at a particular location exceed a certain threshold, usually greater than 90th percentile for at least 5 consecutive days. So the intensity is basically the difference between the actual temperature and the climatological temperature, and it also has a well-defined start and end time. So based on this definition, we use a website that we can use to track the evolution of marine heat waves in near real time. And as you can see on this figure, the South Indian Ocean lately has been under extreme heat stress since April last year, especially in the region east of Madagascar. And the fact that this marine heat wave is so widespread and persistent is usually linked to the developing El Nino, as you can note here from the positive Nino 3.4 index. So this recent marine heat wave is one of the most extreme and long-lasting events that were ever recorded in this region before. And unfortunately, as we've seen with previous similar cases, with the emergence of the strong El Nino, coral reefs and other marine ecosystems in the Western Indian Ocean are at risk. So persistent marine heat waves can cause major impacts on the marine ecosystems. So here in 1998 and also in 2016, during the strong El Nino year, persistent marine heat waves were observed near Seychelles, which caused a widespread coral bleaching in the area. And also in early 2021, drastic changes in the subsurface ocean along the southeast coast of South Africa resulted in massive fish mortality and shellfish. And so apart from these notable cases, there hasn't been a lot of reported incident of ecological impacts related to marine heat waves in this region, and this can be a limitation for this kind of study. So apart from the impact, the direct impact of marine heat waves on the marine ecosystems, marine heat wave can also indirectly impact the coastal communities. So for example, here, in many cases, we've seen that marine heat waves can be an ideal preconditioning factor for passing tropical cyclones. So marine heat waves can fuel the cyclones such that it gain intensity just before it hit land. So in all three regions, we observe an increasing trend in marine heat wave intensity, as well as an increasing trend in number of tropical cyclones. So this implies that tropical cyclones tracking over these coastal zones are more likely to intensify, and they can have devastating impact on the neighboring community. And also on the other hand, a tropical cyclone can end a marine heat wave and bring temporary relief to the coral reefs. So for example, here we have an example of tropical cyclone Kenneth, which co-occurred with a marine heat wave. So we show here that, so in blue, in shaded blue, is the time when both extreme events occur at the same time. So before the tropical cyclone approaches the area, the winds were particularly weak. Heat flux was positive, which means that there was a strong heat gain in the region, and marine heat waves as well as coral heat stress was persistent. But as the tropical cyclone encountered the marine heat wave, the wind suddenly picks up. We have a sharp dropping thermal stress, and the marine heat wave is terminated. So this 1 degree or 2 degree drop in temperature can actually lead to a temporary temperature relief on the coral reefs. So it's really important to monitor marine heat waves in coastal regions just prior to the arrival of a tropical cyclone, for example. So how do these marine heat waves occur? We investigate here a case study in the Mozambique Channel. So this particular event occurred about one month and a half prior to, due to the influence of the positive subtropical Indian Ocean dipole. So when you have positive or warm SST anomalies in the southwest and cool SST anomalies in the southeast, this is one of the drivers of long-lasting marine heat waves in the southern Mozambique Channel. So this warming mainly resulted from atmospheric circulation, so strong insolation and weaker winds contributed to the warming. But what caused the peak in intensity was due to the presence of an anticyclonic eddy. So as you can observe in this animation, the eddy was formed at the coast and it slowly made its way down the channel. So the Mozambique Channel is quite turbulent and has a lot of eddies, and sometimes these eddies, if they are slow moving with temperature that exceed a certain threshold, they may very well cause a marine heat wave. So Clea's talk later will be more on the link between these two and also looking at the subsurface signatures. So as we've seen earlier, at the beginning of the talk, the persistence and high intensity of marine heat waves are usually driven by ENSO. So how does ENSO impact the ocean and atmospheric circulation in the Western Indian Ocean? So to understand this, we basically compare two contrasting events. So El Nino 1998 and one season later, La Nina 1999. And as you may observe, El Nino 1998 was characterized by intense marine heat waves stretching east-southeast. And this is typically due to local processes like less winds, increased solar radiation under less clouds, which limit the evaporative cooling. But a season later, La Nina 1999 do not show any marine heat wave activity, but rather marine cold spells. So this east-southeast propagation is very interesting and is worth investigating. So if we look at the propagation of sea level anomalies, so we look at sea level anomalies across the band 10 to 12 degrees south across the entire basin. So we observed that during 1998, downwelling Rossby wave was present, while during La Nina 1999, we observed upwelling Rossby waves throughout the entire basin. So positive sea level anomalies was initiated at the eastern side of the basin around 1996, 1997, and it reached the western side of the basin after a year. And it was also reinforced near 60 to 80 degrees east due to local wind forcing. So as you can see on this figure, we have a strong positive wind stress curl, which was noted during 1998. And it also strongly correlates with the deepening of the thermocline, which contributed to ocean warming in the region. On the other hand, during La Nina, a season later, the propagation of upwelling Rossby waves, as you observe here, contributed to the strongest negative advection on the record. And if we go back to the winds again, we see that there were anomalous negative wind stress, which reinforced the upwelling Rossby wave as they travel across the Indian Ocean, and therefore cools the upper ocean in the western side of the basin. So how does changes in wind circulation and propagation of Rossby waves impact the Mozambique Channel, especially mesoscale activity in the region? So here we compute the eddy advection in the channel. We compare it with eddy kinetic energy, and we also use an eddy tracking algorithm to look at the frequency of cyclonic and anticyclonic eddies. So during El Nino 1998, there was a northern shift in the southern gyre. So this northern shift led to a more stable current. And due to a stable current, there were less cyclonic eddies that were generated in the region. And this actually helped with the growth of anticyclonic eddies, as you see with positive SLE anomalies. So this actually corresponds with the high number of anticyclonic eddies compared to cyclonic eddies, and also correspond to a positive eddy advection. So in comparison to this, a season later, there was a southward shift in the gyre, which caused a strong instability of the current. So this strong instability leads to large cyclonic eddies in the region. As we observe here, there were more cyclonic eddies compared to anticyclonic eddies, and then there was also the highest eddy kinetic energy observed in this region, corresponding with a strong negative eddy advection. So it's very interesting to see that large-scale climate modes can actually modify the frequency of eddies and also the sizes in the channel. So this can later on influence intensity of marine heat waves in the channel. So to summarize everything, El Nino 1998 also occurred during a positive Indian Ocean dipole, which led to extreme warming in the Western Indian Ocean. So this warming was due to strong heat gain, downwelling Rossby waves, which deepened the thermocline in the west, and therefore there were less cyclonic eddies, but more anticyclonic eddies, which contributed to marine heat waves in the region. So this strong warming also led to a large source of moist air from the Western Indian Ocean that led to strong convection over Tanzania, Kenya, and also Madagascar. But on the other hand, La Nina 1999 was characterized by upwelling Rossby waves, leading to a shallow thermocline in the west and also strong westerly winds, all contributed to cool anomalies and therefore more cyclonic eddies in the channel. So going back to our first figure, this study has enabled us to understand the dynamics that were at play and can also potentially help predicting the impacts in the Western Indian Ocean, especially as associated with ENSO. So thank you. I will hand over to Clea.
Hello.
I'm not sure how to stop this. Oh yeah, okay. Stop share.
So here in my screen. Oopsie. Is my screen good? Can everyone see what's going on? I hope so.
Yeah, we can
Yeah,
see.
it all looks good.
Okay. Hi everyone. Like Matt introduced me, I'm Clea. I'm a very new master's student. I nearly said honors student. And I'm presenting my work from my honors project last year, which I'll be building on for my master's. Oh no, Matt, it's not. Oh, there we go. So my study area falls in the same region as Daneeja's, the Mozambique Channel, or just more south of Mozambique Channel, I think, more, yeah, focused heavily on that region. It's a very dynamic and variable western boundary current. The Mozambique Channel is dominated by the cyclonic eddies and anticyclonic eddies that Daneeja mentioned earlier. And the ocean dynamics play a key role in climate variability and marine ecosystem structure and functioning in this region. And this area, especially along the Mozambique Channel, sustains a diverse marine life essential to the livelihoods and economies of the surrounding countries, which is why studying marine heat waves in this region is so important, because the marine heat waves have significant impacts, like Daneeja mentioned earlier, on the ecosystems and marine health in the region. So yeah, this is just a little bit of literature review. I won't go too much into detail because this is actually mainly Daneeja's work that I built on from last year. But basically, like Daneeja said, as well, and marine heat waves are anomalously warm water temperatures above the seasonally varying 90th percentile, and they have clear start and end dates and last for about 5 consecutive days. So this paper that Daneeja published a while back, I used as my main source of building on from for my research, and she found that more intense, frequent, and longer lasting marine heat waves are present in the southeastern Mozambique Channel, which is the region that I then focused on. And then in this region, severe coral bleaching events have occurred as a result of marine heat waves. So the understanding of marine heat waves is largely limited to surface ocean waters. That's because you need a 30-year climatological period at minimum to identify the marine heat waves based on the definition. And there's just like not enough subsurface data, and it limits the ability to study these regions by quite a lot. But it has been found that marine heat waves can extend to great depths and are known to affect the deep marine environment. There's been a few more papers published on the subsurface characteristics and trends of marine heat waves in recent years. And these papers have also found that predominant drivers of deep and shallow marine heat waves are different. So shallow marine heat waves are normally due to like air-sea heat flux interactions or atmosphere-ocean interactions, whereas the deeper the marine heat wave, the more likely the ocean dynamics play a role in sustaining or driving the marine heat waves. So for my study, my main objectives were to determine the average annual and seasonal surface marine heat wave characteristics and distribution. So I used the surface data for that. And then from this, I built on to investigate the subsurface manifestation of the surface identified marine heat waves. In my thesis, I also discussed the correlation between sea surface temperature variability and the presence of marine heat waves, but I just cut that out for this presentation. So for the surface marine heat wave identification in the study, I used the OISST version 2 quarter degree satellite data set, and then used the Hobday et al. Definition, and that it provides like a MATLAB marine heatwave detect function. My time period was from 1993 to 2022, so that's a nice 30-year time period. And then like I said before, it's quite difficult to get your hands on subsurface data. So for my subsurface investigation, I used the IX21 HR XBT transect, which runs from Mauritius to Durban. This is an opportunistic transect, so the XBTs are deployed off of cruisers and like trade ships, etc. So it's not there's like a scientist on board these container vessels and stuff. The transect is occupied only 4 times a year, so there's only a temperature profile of 4 days that are scattered over a year. So it's not a very precise data set, which was quite difficult to work with, but it still gave us a nice 30-year period of 4 days in a year of temperature data below the surface. And the XBT reached about 860 meters, but for my project it was limited to 800 meters. And so because the XBT data only had 4 temperature profiles available per year, days where surface marine heat waves were identified were cross-correlated to XBT data available days, and then 3 days where surface marine heat waves were identified over the XBT transect were selected as case studies to investigate the subsurface signals of these surface identified marine heat waves. The subsurface temperature anomalies were calculated from seasonal means. So initially, my investigation just looked at the annual surface marine heat wave characteristics in the southern Mozambique Channel. I also cut the XBT line in half just because it was a lot of data to process for an honest project otherwise. And this basically the most noticeable finding here, or most important one for my project, was that over or under the XBT line over here, there is a band of high frequency marine heat waves, but that correlates with a band of shorter lasting marine heat waves, so their duration was low. They didn't reach as high intensity as the rest of the region. As you can see in the third plot, below the XBT transect, the intensity is lower than further south. And then the mean and cumulative intensity was also lower below the XBT line. So this suggests a region where marine heat waves are forming and dissipating very quickly. So they're occurring frequently, but they're not lasting long enough to become extremely intense. But there are still marine heat waves present in this region. Then I looked at the seasonal marine heat wave cumulative intensity, which showed that there wasn't a strong seasonal variability in this region, and the marine heat waves lasted between they had 10 to 30 degrees Celsius per days in this region. So onto my case studies. The first case study I found of a surface marine heat wave that had a subsurface temperature profile from the XBT data was on the 20th of October 2007. The surface marine heat wave extends off the south coast of Madagascar into the Mozambique Channel, and from the temperature anomaly plot, it is evident that there is a subsurface signal, and it extends up to the 800-meter depth, and the temperature anomaly is strongest just below 100 meters. So this suggests that the marine heat wave is intensified below the surface. My second case study was from the 14th of July 2012, and again there's a nice clear surface marine heat wave identified in the middle of the Mozambique Channel that lies over the XBT transect. And there is a distinct positive temperature anomaly below the surface, and again the temperature anomaly is seen to intensify further below surface, so at around 100 meters again. which shows again that or suggests again that the surface identification might be underestimating the true intensity of the marine heat wave below the surface. And then my last marine heat wave case study was on the 9th of January 2020. And here again, pretty similar findings. So there's these distinct columns of warm temperature anomalies below the surface identified marine heat wave. The only thing that's slightly different about this one is that there's a widening of the warm temperature anomaly as you go below the surface. This, we're not sure, this would have to be like further examined, but it could be either a result of the fact that the XBT transect takes about 5 days, I think, to be completed, but as on a transect or as a temperature profile, it is just grouped as 1 day. It shouldn't make too much of an effect, 5 days for temperature, but this could potentially be like an eddy moving across the transect that's being captured here, or it just could be a signal that widens below the surface. So yeah. Then as a final investigation, like Daneeja said, this region is a very high eddy activity region. So I looked at the presence of mesoscale eddies during the 3 marine heat wave case study events. And all 3 of them show that the marine heat wave does align quite nicely with the presence of anticyclonic warm core eddies. So this is a potential driver for these vents. So discussion and conclusion, there was no distinct seasonality in marine heat wave cumulative intensity. The marine heat waves do extend beyond the surface, below the surface, and all 3 of my case studies reached up to 800 meters. And marine heat wave subsurface temperature signal is much stronger than the surface signal. And warm core mesoscale eddies are a possible driver for marine heat waves in this region and may be responsible for the subsurface extent of these events. Also, the presence of the eddies, it's not to say that the marine heat wave that's identified is just a mesoscale eddy, but it kind of suggests that there is a mechanism between the entrapment of these temperature anomalies that become so warm that they become identified as marine heat waves in eddies. So recommendations for future studies, this is kind of where I'm building on from for this year. So a big thing that I would like to build on is being able to analyze the trends of the marine heat waves over time. So that would be by using a ocean model to kind of assess the progression of the marine heat wave over time, instead of only having one day captured for each marine heat wave event. And then the other thing that I couldn't identify from my project was whether there were marine heat waves that only persisted below the surface. So because I had to identify the marine heat waves based on satellite data and then analyze their subsurface characteristics, I wasn't able to do that. So that would be interesting to also examine. And then lastly, to further investigate the drivers of marine heat waves in the Southwest Indian Ocean. So this is particular focus in the relationship between marine heat waves and eddies in the region, because eddies also make a lot of sense as to why the marine heat waves in the region are frequent and less longer lasting, because eddies are moving quickly through the region, carrying all that warm water out or dissipating and forming at a much faster rate than on the eastern side of Madagascar. So yes, thank you. I think that is all.
Cool. Thank you so much, Clea and Daneeja. It's really awesome to have the full overview of drivers and all the way down to the subsurface. I think we have one question in the chat so far. It's not specific to any speaker, so I guess anyone who wants to answer can. So it's from Himanshu, and it's asking, how does one identify if the death of a sea organism is due to marine heat wave and stress. So I guess pinpointing the exact cause of these biological mortalities.
Yeah, so, well, we didn't really go into details into that. It's not really our study focus, but from past studies, we've seen that I think dissolved oxygen is one of the main like culprits. Like when you have high temperature, you have low dissolved oxygen. So I think fish don't have enough to sustain themselves. So that's why you have I mean, large fish mortality, but also the fact that you have quite an abrupt change in temperature. This can cause like hypothermia, for example. So yeah, the fish or other marine organisms can't deal with that. But yeah, it depends on the region. For example, further north, you have cyclones as well that can destroy coral reefs. And yeah, but when you have high temperature, it just like bleaches the coral reefs. It's yeah, compared to when you have a cyclone that just breaks the coral reefs, I suppose.
Right.
Yeah.
And I think I guess it speaks to some collaboration with biologists, because as
Yeah,
oceanographers,
that's what
it's
we really
difficult.
need. Yeah, like a
Yeah,
multidisciplinary study on that.
exactly. Femi, I see you have a hand up. Do you want to ask your question?
Yeah, I have a quick question. Thanks, Daneeja and Clea, for this very nice talk, overview of marine heat waves. So another thing that I've seen a lot of people are doing right now, it's the opposite of marine heat wave, which is marine cold spells. I don't know if you guys have heard of it, and if you have you looked into this a bit in the Southwest Indian Ocean, if there's any evidence of marine cold spells too?
Yeah, we do have. I just showed earlier that like 1999, for example, we didn't have marine heat waves, but we had like that propagation of cold spells that were mainly due to Rossby, upwelling Rossby waves. And yeah, it's something that we need to explore in more details. And Clea, for example, in her master's, she's gonna be looking at cold eddies and the link with cold spells as well. Yeah.
That's great. I see we have another question in the chat from Tando. How do the variations in regional sea surface temperatures affect the frequency and duration of marine heat waves in the Southwest Indian Ocean? And what connections can be made between these events and tropical cyclone activity?
Yeah, that's a very interesting question. In terms of cyclonic activity, I didn't really look into details, but um, like in 1998, for example, the region was quite warm, but we didn't really see any strong tropical cyclone in the regions. But that was because the wind was strong, so it was kind of disrupting the formation of cyclones. But in La Nina events, we saw a few marine heat waves further south, and this actually contributed to the formation of tropical cyclones. So yeah, there's not really like it's not a direct connection between these two events. It's something that we should look into in more details.
Good. And Tando says, thank you. So do we have any other questions? Femi has another question.
Sorry.
No.
So I have a question for Clea. So Clea, you showed this vertical section of temperature along your XPT lines for the subsurface marine heat waves, and then you could see this big blob of positive temperature anomaly. So maybe I've missed it. So the first part I think that I missed was how do you calculate the temperature anomaly? Do you use like World Ocean Atlas mean or?
So I used the XBT transect had a 30-year time period, and then I calculated the temperature anomalies from seasonal means. So I calculated mean for each season and then minus each of the days.
Okay, thanks. Yeah, maybe you mentioned this, but I missed it. But yeah, this it looks quite impressive. It's really such a big big bulb of high temperature, right? Could it also be, so you mentioned something about eddies. So you say it could also be associated with, it could also be like a subsurface eddies, for example, who's trapped a water mass of high temperature and then advecting it from Madagascar towards the Agulhas current?
Yeah, so that's what I'm gonna, I think, try focus my master's on, is further develop the connection between the subsurface temperature anomalies and how they relate to eddies and what that relationship is, because nothing has really been done to investigate that relationship. And like you said, those distinct columns look like eddies, and every time I presented before, everyone's like, how do you know that this marine heat wave is not just an eddy? So it is important, I think, in our region to investigate that further. Yeah, but it is a general, I know other papers have also found that typically marine heat waves intensify below the surface. So it is a general in western boundary currents. So yeah.
Okay, good, thanks.
So,
Yeah.
Femi, following up with your question, so the subsurface eddies, I know like you did a study on that in the Indian Ocean. Is it like more like prevalent from Australia to Mauritius, for example? Does it also goes into the Mozambique Channel?
Yeah, so it moves. So they originate. Well, they don't only originate on the west coast of Australia. So, but a lot of them originate on the west coast of Australia, and then they propagate all the way towards Madagascar. But of course, south of Madagascar, you have the East Madagascar current, the East Madagascar retroflexion, which could also create some eddies. But these eddies, you would expect to see them from satellite data. But the subsurface eddies, yeah, so that would be surface, yeah. At least they could also be subsurface eddies, but with a surface signature. So you from just trophic velocities from Aviso data, you would see it. But there could also be subsurface eddies which do not have a signature in the surface. And but I haven't looked south west of Madagascar, but maybe there are. I can't really say, but it really looked like a nice, really nice eddy structure. That's why I was wondering. Yeah.
Cool. Thanks. Daneeja, I've actually got a question just going back to the relationship between cyclones and the marine heat waves. I find it fascinating because on one hand, the marine heat waves potentially could intensify the cyclones, but at the same time, the cyclones, if I get it right, can also break a marine heat wave. So my question is, so when you see a cyclone passing over these marine heat waves, is it a temporary just drop in the surface temperature, or is the event itself kind of broken or finished? So is it a temporary stop?
Yeah, I think it really depends on how close the cyclone is with the region. If also it depends on the winds, the strength of the winds as well. If it's strong enough, then of course it will just cool the water column entirely. So this might disrupt the marine heat wave like permanently. But we've seen a lot of cases where like just passage of tropical cyclone quickly over the region will just temporarily cool the water, the surface water, but not, like it will come back again later. So it really depends on the strength of the winds and also how close the cyclone is with the region.
Okay, great. Yeah, I find it very, very interesting that you have both sides of the impact.
We've seen that like if it exceeds, for example, a certain wind threshold, like 0.015, it definitely disrupts the cyclone, like permanently. So it's something that we need to look into in more details. Yeah.
Okay, great. So are there any other questions from any of the participants? Okay, it looks like we don't have any more questions. I'm just going to use this opportunity. I have one more question. I'm sorry, this was the last one. But I was wondering, so as eddies, as drivers of these extreme events, are there case studies of the eddies advecting these extreme events? And is that a study that's been done?
No, I think there's like a lot of people want to do that study. I think they want to use an eddy tracking algorithm to just track these eddies and see if it corresponds with like marine heat waves as it propagates. But maybe it's something that Clea could do. But I haven't seen any studies on that as yet.
Okay, because that would be very interesting, and potentially in the subsurface as well, if these eddies then advect these warm anomalies down, potentially down the channel.
Yeah, I think we'll have to use a mixed layer heat budget to really see the contribution.
Okay. Well, that's a lot of extra work for the future, which is very exciting.
The list of things to do is getting longer and longer.
Yeah. Yeah. Okay. So I think that concludes our seminar for today. And I just want to thank our speakers again. Thank you so much for your time. And thank you for everyone for participating. And the next seminar is going to be on the first Friday of April. So looking forward to see everyone there. Thank you.
Thank you, Matt. Thank you, everyone.
Thank you. Bye.